Hi, my name is Dr. Nazma Hasey. I'm currently the lecturer for the module Linear Algebra Geometry 1 here in the Maths department at King's. So this is a first year module and it's taught in the first semester. So if you end up coming here to do maths, I'll probably be one of the first people that teaches you. So this module covers a lot of very foundational and core topics in maths that underpin a lot of work that you'll do in the future. So the content that we do here will probably be used again and again and again in essentially all of your subsequent modules. Now, some of the objects that we study may be familiar to you already. So in particular, we'll do a very detailed study of vectors and matrices, which a lot of people will have covered already. But don't worry if you haven't, because we will review all of this. The difference, though, is we'll study this to a far greater depth than you probably will have already done so, and we'll also do it in a far more abstract setting. So not only will we learn a lot of new techniques and a lot of ways to solve problems with them, but we'll also learn why these techniques work, why things are defined how they are, and also how these concepts relate to other areas of maths. So to give you a better idea about the module, I just want to give you a very informal explanation of one of the main themes. The primary object of study in linear algebra and geometry is a linear transformation. So first of all, a transformation is just another word for function. We think of it as something which just transforms an input to produce some output. Now, the key word in this sentence is linear. So a transformation is linear if it satisfies a couple of properties. So the first of these is that if I scale the input by some constant factor, then it produces a corresponding scaling in the output. So in other words, if I double the input, I double my output. If I triple my input, I triple my output. If I multiply the input by a half, I multiply the output by a half. So the second property is that if I add two inputs, this just leads to addition of their respective outputs. So in other words, if I add two inputs and then transform them, the result will be the same as if I had transformed them separately and then added the resulting outputs. In applications and in the real world, most transformations that you encounter are not linear, but they can generally be approximated very well by linear transformations, and so we can still use all our theory and techniques that we develop for linear transformations to solve problems in those cases. So let's look at some examples. So the first example I want to look at is just a transformation from real numbers to real numbers given by f of x equals 3x. So this is linear, so this transformation just triples the input. So let's check that this is linear. So what happens if I scale the input by some constant factor, let's say c? So I want to work out what f of cx is, where c is just some constant. So this transformation triples the input, so this is just 3 times cx. But of course, this is the same as c times 3x, but 3x was just f of x. So this is just c times f of x. So we see that if I scale the input x by a constant, then I scale the output f of x by the same constant. So what happens now if I add two inputs? So let's evaluate the sum of two inputs, x and y. So again, I just triple this, so I get 3 times x plus y. And I can split this up to get 3x plus 3y. But this is the same as f of x plus f of y. So again, I've added two things on the input and transformed them, and the result is just f of x plus f of y. So this really is linear. Now let's look at an example of a nonlinear map. So f of x equals x squared is not linear. So how can we see this? Well, let's test it out. Let's try and scale by some constant, for example, 2. So what's f of 2 times x? So I'm going to multiply the input by 2 and see what happens. So then I square the input. So this is 2x squared, which is the same as 4 times x squared. So notice this is 4 times f of x. So in other words, I've doubled the input. So I've scaled the input by 2, and the result is that I've scaled the output by 4. But for it to be linear, I have to scale by the same amount. So in other words, doubling the input leads to quadrupling the output. So this is not linear. So the next example we'll look at initially is the function f of x is equal to 2x plus 1. So let's see if we can determine whether this is linear. So let's try the same thing again. Let's try and scale the input by a constant factor. So let's choose 2 again and see what happens. So f of 2x, well, I substitute 2x into the equation above, so I get 2 times 2x plus 1. And this is the same as 4x plus 1. So now let's work out what 2 f of x is, because we need them to be equal if this is a linear map. So 2 times f of x is equal to 2 times 2x plus 1. And when we multiply this out, we see that this is 4x plus 2. Now these are not the same. So the first one has a plus 1 on the end, and the second has plus 2. So these are not equal. So this transformation is not linear. So even though its graph is a straight line, and so many people refer to it as a linear function, it is not really linear in the precise sense of the word that we've got here. In these examples, the inputs and outputs of our transformation have all just been numbers. But actually, we can think about linear transformations more generally. So we can have linear transformations where the inputs and outputs are not just numbers, they're more general objects. But in order for our definition to make sense, we need our inputs and outputs to satisfy certain properties. So in particular, we must be able to do the following. Of course, we have to be able to scale the inputs and the outputs. So remember, scaling here just means multiplying by numbers. So I have to be able to multiply by all numbers. The other thing we have to be able to do, of course, is add our inputs or add our outputs. If we can do these two things, then we can make sense of linearity. So a collection of objects with these properties has a very special name, and we call it a vector space. And the elements of our vector space, we refer to them as vectors. Let's look at an example of a vector space, which many people will be familiar with. So the vector space we'll look at is the set of all possible pairs of numbers. So we'll write this as a column, sort of x, y, where x and y are just numbers. So for example, 3, 1, or -1, 1/2, or even √7 and pi, as long as I just have two numbers. So when we write them in a column like this, we usually call them column vectors. So let's justify that this really is a vector space. So first of all, these column vectors can be scaled. So for example, if I want to scale, let's say 3, 1 by a factor of 5, well, I just scale each component. So I just get 15 and 5. They can also be added. So if I want to add together two vectors, 3, 1, let's say, and -1, 1/2, then I just add the corresponding components. So I just get 2 and 3/2. We can also think about these geometrically and represent them as points or arrows in the plane. So the vector xy, I just represent it as a point with coordinates xy in the plane. Or alternatively, I think of it as the arrow going from the origin to that point. A popular but mathematically inaccurate definition of vectors is as objects that have magnitude and direction. So while this is correct in some contexts, so for physical vectors, this is not true in general and so can be misleading. So to be clear, in general, vectors are not defined by having magnitude and direction. This is not true for most kinds of vectors. So let's look at a couple of examples of linear transformations on our vector space. So the first transformation we'll look at, which I'm going to call T. So I'm going to write T for my transformation, and it's just going to take my entries and swap them. So I'll put Y upstairs and X downstairs. So let's just check that this really is linear. So let's scale our vector by a constant, which I'll just call C. So this transformation just swaps the two entries. So I get cy at the top and cx at the bottom. But this is the same as c times the vector yx. But yx was just my original output, so this is the same as c times t of xy. So okay, I've checked scaling. So now I need to check what happens when I add two vectors. So let me take two vectors, x1, y1, and x2, y2, and I want to add them, and then I want to transform them and see what the result is. So first, let me add them. So if I first add them, then I will have t of x1 plus x2 at the top and y1 plus y2 at the bottom. So when I transform, I just swap the entries again. So this is just y1 plus y2 at the top, and then x1 plus x2 at the bottom. But I can split this up again, and I get y1 x1 plus y2 x2. And again, each of these just correspond to the output from x1 y1 for the first one and x2 y2 for the second one. So the result is just the sum of the output corresponding to my two vectors. So this really is a linear transformation. Let's look at one more example. So this time my transformation will take a vector xy and it will sum the coordinates and put them at the top and look at the difference x minus y and put it at the bottom. So this is my transformation. So let's do the same thing again and let's see what happens when I scale my input. So I look at what happens to cx and cy. So now I sum the two coordinates at the top and look at the difference at the bottom. So I get cx plus cy and cx minus cy. So I can take out a c common for each component. So I get c times x plus y and c times x minus y. Then I can just pull out this constant factor. So I get c times the vector x plus y, x minus y. But again, this is just my original output from xy. So I check that I do just end up scaling the output. So now let's again check what happens when I sum two vectors. So I'll do the same thing as before. I'll take x1, y1 and x2, y2 and sum them and then transform. As before, this is the same as t of x1 plus x2, y1 plus y2. So the output that I get this time, in the top, I'm going to get the sum of those two coordinates. So I'm going to get x1 plus x2 plus y1 plus y2. And in the bottom, I'm going to get the top coordinate minus the bottom one. So I get x1 plus x2, the top coordinate, minus y1 minus y2, so minus the bottom coordinate. Now I can split this up to get x1 plus y1 on the top and x1 minus y1 on the bottom. And on the other one, I get x2 plus y2 and x2 minus y2. So just as we had before, each of these is just one of my original outputs. So this is the same as t of x1, y1 plus t of x2, y2. So this shows that this transformation is also linear. So if you want to test yourself on any of the ideas that we've talked about in this informal introduction, then do please have a go at the quiz that comes along with this. Okay, thank you very much for watching.